Welcome, physics students, to this section on elastic and inelastic collisions. We are going to talk about perfectly inelastic collisions, and then we'll talk about elastic collisions, and then we'll look at the conservation of momentum in different kinds of collisions, and whether or not kinetic energy is conserved in different kinds of collisions. Let's start with perfectly inelastic collisions. A perfectly inelastic collision is when two objects collide and then move together as one mass. An example would be the arrows and the target. This collision is called perfectly inelastic. Another example would be if a meteorite collides head-on with Earth, becomes buried in Earth, and the collision is nearly perfectly inelastic. Here is another example of a perfectly inelastic collision. Granny collides with little toddler, and the two move along as one mass. When we talk about perfectly inelastic collisions, we can use this equation, which should make sense. We're talking about the individual momentums of the two objects prior to the collision. So that would be their initial momentums. We add those together, and that should equal, and in the end, the final velocity of the two, because they are moving along as one mass, but we will need to multiply that by the sum of their masses together. So what is the final velocity of Granny and toddler together? Pause the video and see if you can figure that out. So if you said the final velocity of Granny and toddler together is 4 meters per second, then you got it right. If not, take a look at this and see where you might have gone wrong. I chose Granny as being object 1 and the little toddler as being object 2. An important note on inelastic collisions is that the total kinetic energy is not conserved in perfectly inelastic collisions. It does not remain constant when the objects collide and stick together. That's because some of the kinetic energy in the collision is converted into sound energy, internal energy, thermal energy, as those objects deform during the collision. That phenomenon helps us make sense of the words elastic and inelastic, because oftentimes when we think of the word elastic, we think of something that can return to its original shape. And in physics, the most important characteristic of elastic collision is that the object maintains their original shape. They are not deformed by the action of whatever the forces are acting on them. So an object in different objects that are involved in inelastic collisions are deformed during that collision, and they lose some of their kinetic energy. Not necessarily all of it, but some of it. And you can calculate the kinetic energy using the formulas that we have already learned for kinetic energy. So let's look at an example, a problem using kinetic energy and in perfectly inelastic collisions. Let's say we have two clay balls that collide head-on in a perfectly inelastic collision. The first ball has a mass of 0.500 kilograms and an initial velocity of 4.00 meters per second to the right. I'm going to go ahead and write down those things that I know. Since the velocity is 4 meters per second to the right, I'm going to indicate that with a positive sign. My right-hand side will be my positive side. Now, the mass of the second ball is 0.250 kilograms, and it has an initial velocity of 3.00 meters per second to the left. So I'm going to indicate this velocity with a negative number. Now, the questions that I'm being asked is, what is the final velocity of the composite ball of clay after the collision? And secondly, what is the decrease in kinetic energy during the collision? So to find my final velocity, I'm going to use my equation for perfectly inelastic collisions that we just learned. And I'm going to plug my values into that equation and solve for my final velocity. This will be the variable that I am solving for. That will answer this question. So I have my mass 1 times initial velocity 1 plus mass 2 times my initial velocity of 2. Of course, it's negative. And I'm going to write this on 2 lines. Sorry about that. Kind of ran out of room. And I add the masses together. And after I add them together, multiply it by the final velocity. When I plug all these numbers into the calculator, do my little algebra, I end up with a final velocity of 1.67 meters per second. And it's a positive number, so it will be to the right, since that is what I indicated as the direction for a positive number. Now, to calculate my change in kinetic energy, I can simply look at the final kinetic energy minus the initial kinetic energy. And that will give me my change in kinetic energy. Realize that for determining my kinetic energy, my final kinetic energy, I need to look at both objects. So my final kinetic energy will be composed of 1/2 mv squared final for my mass 1 and velocity, for object 1, plus 1/2 mv squared final velocity squared for object number 2. Then I can subtract the sum of all of the kinetic energy initial. So that would be the kinetic energy for both objects. And there I wrote that down, both for object 1 and for object 2. Now I'm ready to substitute values in for these variables. My mass for object 1 is 0.5. My final velocity for both objects is 1.67. I square that, plus 1/2 times the mass of object 2 times that final velocity as well squared. And I'm going to say minus, and I'm going to write this second term here, down here. When I substitute all of the values in and punch that into my calculator, and I apologize, normally I would write all of the units, but there just wasn't really enough room on the screen to do that, so I omitted the units this time. But my answer ends up being negative 4.07 joules. That is the change in kinetic energy. So that represents the amount of kinetic energy that was converted into some other form of energy during this inelastic collision. Now let's take a look at elastic collisions. For elastic collisions, two objects collide and return to their original shapes with no change in total kinetic energy. After the collision, the two objects move separately. For elastic collisions, momentum and kinetic energy remain constant. So the total momentum and the total kinetic energy will remain the same in elastic collisions. These are the equations that we can use for elastic collisions because, again, our kinetic energy will remain constant for these kinds of collisions. So let's look at an example of an elastic collision. Let's look at, say, pool balls or bowling balls, some kind of balls that are headed toward each other. Ball A has a momentum of A and ball B has some momentum of B. They are heading in opposite directions. After our initial step here, where the balls are approaching each other with individual momentums, we have our impulse step, and this should look familiar. Here's the impulse term, and that represents our change in momentum. We're going to have some change in momentum here for ball A and some change in momentum for ball B. Of course, it will be equal in force and as well as time duration, and opposite in direction from the momentum of A. That leaves us with our final step, where we have both objects returning to their original shapes and moving separately after the collision, with a momentum for A and a separate momentum for B. So in the real world, most collisions are not perfectly inelastic, and Likewise, they are also not elastic either. Most objects do not stick together after their collision, so they move as one. And most objects actually lose a little bit of kinetic energy. If you think about collisions that we have considered to be elastic collisions, such as kicking a football or billiard balls hitting each other, those are not perfectly elastic. If you think about a football's foot or a football player's foot kicking the ball, there is some deformation of that football, and some kinetic energy is lost there. As likewise, billiard balls, when they hit one another, they make a little clicking sound. Well, that some kinetic energy is lost to that clicking sound. In fact, whenever there's a sound, some kinetic energy is lost. For the purposes of our class, however, we are going to consider all collisions in which the objects do not stick together and are perfectly inelastic. We will consider those to be elastic collisions. However, most collisions do fall into this category in between perfectly inelastic and elastic, and we call it simply inelastic collisions. And that would be where the two objects deform during the collision, so that there is some total kinetic energy loss, but the objects then move separately after the collision. So let's work on a problem that involves elastic collisions. Let's say that a 0.015 kilogram marble is moving to the right at 0.225 meters per second and makes an elastic head-on collision with a larger 0.030 kilogram shooter marble right here that is moving to the left at 0.180 meters per second. I'm going to stop and write down a few things that I know already. So I have my masses here. I'm calling this ball 1 and this ball 2. The smaller one is 1. And since it is moving to the right, its initial velocity will be positive, and since this larger ball is moving to the left, ball number 2, that initial velocity will be negative. So after the collision, the small marble moves to the left at 0.315 meters per second. I'm going to write that down as negative because it is moving to the left, and it is the velocity of marble 1 final. So we're going to assume that neither marble rotates before or after the collision, that both marbles are moving on a frictionless surface. So what is the velocity of the large marble after the collision? So this will be my unknown. I'm looking for V2 final, and I can use my equation for the conservation of momentum to find the final velocity of that second larger marble. There's that equation. And now I can simply plug my numbers in, and this is a pretty easy plug-and-chug problem. Here are the numbers that I've plugged into the left side of the equation. Now I'm going to plug in the numbers for the right side of the equation, and I'm going to write that down a line below so that I have enough room. And there I have plugged all my values in for my different variables. I can simply solve now algebraically for my velocity of the second object, the final velocity. And when I do that, I get the velocity for my second object, the final velocity, is 9.0 times 10 to the negative 2 meters per second. Since it's a positive number, the direction will be to the right because that is the direction of a positive velocity. Here's some advanced ideas. Please feel free to ask your own questions, come up with other ideas that aren't on here, and bring those to class, and I look forward to seeing you.